Yeah, welcome. So the topic we'll be discussing in this lecture is inference in first order logic. So in the last lecture we have discussed like how a knowledge base can be constructed for a first order logic. So basically we have discussed something called as knowledge engineering. So so in this lecture we'll be discussing like how we infer things with first order logic. Previously we have discussed like inference in proportional logic. Similarly, how something can be inferred with first order logic. That's what we are going to discuss. So these are the topics we are going to discuss here. First is the technique called reducing the first order inference to proportional inference. So in this technique, what we are going to discuss is the statement in first order logic, whatever the statement which is in first order logic, we will convert it to proportional logic. The statement in first order logic will be converted to proportional logic, and then we will apply the inference technique of proportional logic. That's it. So here we are not directly going to infer the first order logic. Rather, the sentences in first order logic will be converted to proportional logic. Then we apply the standard inference procedures which are available in proportional logic for inferring. So this is the first method. But this method is not much effective. Hence, we'll be discussing one more method of inference which is called as unification. And also we'll be discussing another method which is called as generalized model exponents. And then how inference in first order logic is done using forward chaining, backward chaining, and resolution. All these things we'll be discussing. So if you recall, we have discussed all these things with proportional logic. With proportional logic, how we apply resolution, what is forward chaining, backward chaining, all these we have discussed. Now the same thing we'll be discussing for first order logic. So that's the brief overview. So to start with, first we'll be discussing this first concept, which says like how inference can be, mm, how we infer the first order logic by converting it to a proportional logic. So to convert the first order logic to proportional logic, the main thing is the main thing what you want to convert. So the main difference between the first order logic and proportional logic is the first order logic involves quantification. It contains universal quantifier and existential quantifier. So we have two rules which is used to remove the universal quantifier. So first we'll be discussing a rule called universal instantiation. This rule is to remove the universal quantifier. This rule, universal instantiation, is used to remove the universal quantifier for all. And there is another rule which is called as existential instantiation, and this rule is to remove the existential quantification. So first let us see how the universal quantifier can be removed from the from any statement which is represented in first order logic format. So we'll start with universal instantiation. So this is how it is defined. Every instantiation of a universally quantified sentence is entitled by it. So how can we remove the universal quantifier? So if we have a universal quantifier, something like this, for all v alpha, where alpha is a sentence, alpha is a sentence, v is a variable. So if you have a sentence something like this, for all v comma alpha, where alpha is the sentence and v is the variable, then the universal quantifier can be removed by repeatedly replacing this v with a ground term in the sentence alpha. So universal quantifier cannot be removed in one go. You have to repeatedly do that. Why? Because this is a variable. Because universal quantifier basically it includes a variable, and the variable may take multiple values. It may not take a single value. It may take multiple values. So the rule should be applied again and again until all the possible values or all the possible ground terms can be applied for this variable v. Okay, so this is the whole concept. So if you have a sentence something like this, for all v comma alpha, where v is a variable and alpha is a sentence, then repeatedly apply universal instantiation by replacing v with a ground term. in the sentence alpha. Okay. So here we'll have an example to clarify. So here v is a variable, whereas g is a ground term. Okay. So here is an example. For all x, king of x and greedy of x implies evil of x. That is, for all persons, if that person is a king and if that person is greedy, then it means that he is evil. So now if you apply universal instantiation on this, then how it will happen? So say let us assume this is a knowledge base, and this knowledge base contains, so for all x, so x represents what? X represents some object, some individual. Okay. So this knowledge base contains these possible values for x. It can be x can take the value of John, or x can take the value of Richard, or x can take the value of father of John. So these are the possible values this knowledge base hold for x. If your knowledge base contains more values, then you have to apply more, you have to apply the rule again and again. So we assume that our knowledge base contains only these three objects which can take the value of x. Hence we apply the universal instantiation only three times on this. So when you first time when you apply, then we replace, so this is v, x is a variable, we replace v with one of the ground term. So these are ground term. John is a ground term, Richard is a ground term, father of John is a ground term. So when you apply for the first time, x will be, the variable x will be replaced by the ground term John, and hence we get king of John and greedy of John implies evil of John. So here there is no quantification, right? When you apply it for the second time, now we replace x with the ground term Richard. So we got king of Richard and greedy of Richard implies evil of Richard. And again, when we apply for the third time, the variable x is replaced with father of John. So king of father of John. So that means father of John is a king, and father of greedy of father of John, which means father of John is greedy, which means father of John is evil. That is evil of father of John. So if you have more variables, if you have more ground terms, if you have more ground terms in the knowledge base, this rule should be applied again and again for all those ground terms. Okay. So this is how universal instantiation works. So basically, with universal, so if you want to remove the universal quantifier, so why do we remove this? Because by removing, we can convert the sentence to one. We can convert a sentence in the first order logic to a proportional logic. So when you want to remove, the variable should be replaced by the respective ground term, and probably you have to replace it for multiple times. Okay. So this process is called as universal instantiation. Fine. Next, we will be discussing something called as existential instantiation. So this is which is used to remove the existential quantifier. So again, let us assume there is a sentence like this. So this line should come here. Okay. So let us assume there is a sentence like this. There exists v such that alpha. So alpha is the sentence. So that sentence contains uh, some some variable v. Okay. Here what we do, here in the previous case, for removing the universal instantiation, the variable will be replaced with a ground term. But for removing the existential instantiation, the variable should be replaced with a constant. So we replace the variable with some unique constant. The constant should not be repeated. The variable will be replaced with some constant in the sentence alpha. Here we apply the rule only once. We don't apply repeatedly. Okay. So repeated application happens only for removing the universal quantifier. Here you should apply only once. You should not apply repeatedly. And this variable here we are going to replace with a constant. This k represents a constant, and this constant should be a unique constant. So here is an example. There exists x such that x is a crown and x is on the head of John. So if you want to remove the universal existential quantifier here, now this variable x should be replaced with some constant. So instead of x, we are using the constant c1. So we are saying that crown of c1, which means that c1 is a crown. Okay. And on head of c1 comma John, which means that c1 is on the head of John. Okay, right? So uh, so 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 here you should apply the rule only once. Okay, why we are saying that you should apply the rule only once? See, if you apply the rule second time, what will happen? Assume we are applying the rule for the second time. So now crown of, now we should not use the same constant. So say that I'm using some other constant c2, crown of c2 and on head of c2 comma John. Now the it becomes meaningless. See, now you are now this statement, what it says, the first statement says that there is a crown c1, one particular crown is called a c1, and that crown is on the head of John. Now again you are telling that there is some other crown c2, and that is also on the head of John. There is only one crown, right? John can have only one crown at a time, so he cannot have both the crowns. Because of this reason, we are saying that this, when you apply the existential, uh, when you perform existential instantiation, it should be, the rule should be applied only once. Here it will not make sense if you apply multiple times, whereas for universal instantiation it should be applied for multiple times. Okay, and why are we saying that this constant should be unique? So this, we are saying that this constant should be unique because assume that there is another sentence something like this: there exists x, crown of x, and on head of, x comma Richard. Okay, now assume that for the first sentence is crown of x and on head of x comma John. So for the first sentence, for removing the existential quantifier by applying existential instantiation, we have replaced this x with c1, right? Okay, now when assume that I want to apply existential instantiation for this rule. So when you apply existential instantiation for this rule, you have to use a different constant. You cannot use the same constant. When I use a different constant, I will get a sentence something like this: crown of c2 and on head of c2 comma Richard, which means that c2 is a crown and c2 is on the head of Richard. So it is very clearly saying that c1, see, the crown c1 is different from the crown c2. They both are different objects. It's an object of same type, but they are different copies, right? So c1 is a crown which is on the head of John. C2 is another crown which is on the head of Richard. It's very clear. But if you use c1 here also, then what will happen? Then it creates ambiguity. Then first you are saying that the crown c1 is on the head of John. Then again you are saying that crown c1 is on the head of Richard, which cannot happen, right? Hence we say that when we remove the existential quantifier, it should be replaced with a unique object. The variable should be replaced with a unique object, and the rule should be applied only once. It should not be applied multiple times. I think it's clear. So this is how we remove the existential quantifier. Once you have removed the universal quantifier and the existential quantifier from the sentences, then you will get, then your knowledge base will have the sentences which will be in uh, which will satisfy the format of, which will be satisfying the format of propositional logic. Okay, so initially if you have these sentences in the knowledge base which is of first order logic, then after applying universal instantiation and existential instantiation, then you will get sentences like this: king of John and greedy of John implies evil of John. King of Richard and greedy of Richard implies evil of Richard. So now already your sentences are converted to propositional logic. So this process of converting the sentences from first order logic to propositional logic is called as proportionalization. So this is called as proportionalization. So now we have created, this is the original KB. This is the original KB, that is knowledge base. Now this is the new KB. So this is the new KB with, after proportionalization, right? So here the proportional symbols, these are the proportional symbols. King of John, greedy of John, evil of John, all these are proportional symbols. Okay. So now after converting to proportional symbols, we can directly apply, we can directly infer by using the like how we infer things in proportional logic. So basically every first order logic knowledge base can be proportionalized so as to preserve the entailment. So so the idea is to proportionalize KB, that is convert the knowledge base in first order logic to proportional logic, and then query and apply resolution. So basically after that you follow, you apply inference, like how you apply inference in a proportional logic. So that's the whole concept is. Okay, fine. But what's the problem with proportionalization? So why are we discussing? So in the introductory part I said that we'll be discussing but some more techniques for inference in first order logic. So there is some problem with proportionalization. The problem is the proportional logic, the proportionalization, the process of proportionalization, it seems to generate lots of irrelevant sentences which are not required. So that is one of the problem with proportionalization. Uh, so basically it does not, uh, the process is complicated. The when you convert a first order logic to a proportional logic, it creates more sentences, or it's a lengthy process, hence it creates a lot of irrelevant sentences, right? Okay, for example, if this is your initial knowledge base, and if you want to convert this to proportional logic, because here there are universal quantifiers are here. So this is slightly different from the previous one we have discussed. Okay, here if you see, for all x king of x and greedy of x implies evil of x, this sentence is same which we already discussed, which means that if somebody is a king and somebody is greedy, then they are evil. And now here we are saying that John is a king. John is a king. We are not telling anything about uh, greediness of the John. Okay, there is no specific statement about the, about whether John is greedy or not. But there is another statement included in the knowledge base which says that for all y greedy of y. So basically, this statement means that everyone is greedy. Okay, so basically, this statement means that everyone is greedy. So when you say that everyone is greedy, then John is also greedy. Okay, and the first rule says that if somebody is a king and somebody is greedy, then they are evil. So this third rule says that everyone is greedy. So John is also greedy. And the first rule say, and the second rule says that John is a king. So John is also evil, right? Okay. And the last rule says that Richard is the brother of John. Right? Now assume that you are querying the database. You are querying the database like uh, who is evil, evil of like who is, with this info you are querying the database like who is evil. So evil of x is what, right? So from this it is very obvious, as a human you can see that it is very obvious that John is evil. The answer is John. The answer should be John of evil. Okay, or the sorry, the answer should be evil of John, that is John is evil. So this is the answer. It seems very straightforward, but actually if you apply proportionalization, then what it will do, it has to first create the rules. First it will uh, it will create all those rules. So greedy of y means everybody is greedy. Okay, so it will create rules like it will create sentences like greedy of John, and also it will create sentence like greedy of Richard. Okay, right? And then and then it will create like king of John and greedy of John, which implies evil of John. So it has to go through all these steps to identify whether John is evil or not. So in that process, it is creating many unnecessary statements like greedy of John, greedy of Richard, like that, which is not required. Our knowledge base contains only 2 ground terms, that is fine. But if your knowledge base contains 1,000 ground terms, so there are 1,000 such persons, John, John, Richard, Joseph, something, hundred or thousands of names, then it will create all those things, greedy of X, greedy of Y, everything it will make, which is irrelevant, which is not required, and it is time consuming. Hence hence we say that uh, this is hence we say that the process of proportionalization, it creates many unnecessary sentences. So basically this is the drawback with proportionalization. To overcome this drawback, we are going for some other techniques, right? So we are going for a technique called unification. So with unification, we can directly infer things from first order logic. So that's the beauty of unification. So with unification, you need not convert the first order logic to proportional logic. Rather, directly we can infer from first order logic. Okay. So how unification works, we'll discuss here. So we can get the inference immediately if we can find a substitution theta such that king of x and greedy of x matches. Okay. So here we are going to substitute x with theta such a way that it should match both king of x and greedy of x. Right. Okay. So such that king of x and greedy of x match king of John and greedy of y, something like that. Okay, because as per our new rule, it is greedy of y, which means that everybody is greedy. Right? So theta will be replaced with, so theta here, theta is what? So in our original rule, if you see, I mean here we are having for all x king of x and greedy of x implies evil of x, and for all y greedy of y. So x we are taking from here, y we are taking from here, because this x can be anything. So this uh, once you solved this, then you know that everybody is greedy, right? So we are taking this y from here. So theta is what? Replace x with John. That is in the first rule. Here 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 replace x with John, right? So that is what it says. Theta equal to x slash John means it says that replace x with John. So basically here we say that x should be replaced with John and y should be replaced. I mean here uh, in king of John, sorry, in king of x, x should be replaced with John. In greedy of y, y should be replaced with John. So when you do that, so that is what is called as theta. That is what is called as theta, right? So this is one example, but definition for unification is, if you have two sentences, if you have two sentence, if you have a sentence alpha and beta, and unification of alpha and beta is equal to theta, that is using theta you can unify alpha and beta. Under which condition? If 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 alpha theta is equal to beta theta, right? That is so theta is what basically we are replacing something in alpha, okay, and we are replacing something in beta. We are replacing something in alpha and we are replacing something in beta. So what we are replacing, that is defined through theta. So theta includes the replacement part of alpha, and also it includes the replacement part of beta. Here you can see, right? So it includes the replacement part of the first sentence and also for the second sentence. So this means that that first sentence x is replaced with John, and in the second statement or in the second sentence y is replaced with John, right? So after replacing, so some part of theta, that is theta is not a simple statement, theta is a complex statement because it contains many things, right? So some part of theta goes to alpha, some part of theta goes to beta. Are you getting? So after replacing, we say alpha theta should be equal to beta theta, then only it is said to be unified, right? So only if that condition is satisfied, is called that as unification. Otherwise it is not called as unification, right? So if you can find such a theta, then that is called as unification. Okay, fine. So with this understanding, let us discuss some examples. Okay, so let us discuss some examples, right? Okay, so for example, let us consider this statement. Say this, you can, this is first statement which says that knows of John comma x. So basically this statement means that John knows everyone. So the statement means that John knows everyone. Okay, and there is another statement which says that John knows Jane. John knows Jane. Here you have only one variable, that is x. Here you have only one variable, that is x. So now what will be our theta? Now our theta will be, x can be replaced with what? X can be, here our theta will be, x can be replaced with Jane. So if you replace x with Jane, then these two statements are same. This also says that John knows Jane, and this also says that John knows Jane. Both are same, right? Okay. Now this is what, now after replacing this, this can be called as p theta. And this here there is no replacement, but still you can call it as q theta. Okay. But if you see the second sentence, it is John knows everyone. So this statement says that John knows everyone. And the second statement says that everyone knows OJ. Okay. First statement says that John knows everyone, and the second statement says that uh, everyone knows OJ. Okay. So here how we will replace? Here what will be theta? Finally, we should make this two sentence same. We should unify this. That is what our meaning. So x should be replaced with what? So in this case, x should be replaced with OJ. X should be replaced with OJ, and y should be replaced with John. Okay. So when you replace x with OJ, so this becomes OJ. So it means John knows OJ, right? And when you replace y with John, and when you replace y with John, so this also becomes John knows OJ. Okay. So again, both these sentences are same, right? So this is called as unification. Similarly, here if you see, John knows x, okay, John knows x, and y knows mother of y. That is, y knows his own mother. John knows x, and y knows mother of his own mother, right? So here first let us uh, first let us how let us see how we will replace y. Okay. So you can replace y with John, right? So when you replace y with John, this becomes John. Okay. So John knows mother of y. Again, here also you replace y with John. So John knows mother of John. It is John knows his mother. That's what it says, right? Now x should be replaced with what? X should be replaced with mother of y. Basically, x should be replaced with mother of y. But what is y? Y is John. So we can say that x should be replaced with mother of John. Okay. So x should be replaced with mother of John. So when you replace x with mother of John, again it says that John knows mother of John. So this is also John knows mother of John. So both are same, right? So these are some of the typical examples for unification. But if you see the last statement says that John knows everyone, and everyone knows OJ. Okay. But here actually this statement will fail, because here we are using same variable. Both are x. This is also x. This is also x. So now you cannot say that if you can replace either x with John or x with OJ. If you replace x with John, then this will become John knows John, and this will become John knows OJ. Then they both are not same. Are you getting? If you replace John with OJ, then this will become John knows OJ, but this will become OJ knows OJ. That is me. I mean, then these two sentences are not same. They are not unified. So this last sentence fails. Why it fails? It fails because same variable is used in both the sentence. Hence, it is failed. So if you want to make it successful, you have to change one of the variable, right? So if you change one of the variable, then this statement also we can unify. For example, this second statement, if you convert like this, knows of z17 comma oj. So z17 is just a variable. So instead of x, we are using z17, right? Now what you can do? Now x can be replaced with oj, and z17 can be replaced with, now, now x can be replaced with oj, and z17 can be replaced with John, right? So this x becomes oj, and z17 becomes John. So now the meaning is John knows OJ and John knows OJ. Both are same, right? So this is the process of unification. So basically, with unification, we can mm, directly perform inference from first order logic without the need to convert it into proportional logic. That is, we need not go through the process of proportionalization. So that's the key with unification, right? So whatever we have discussed, that's what explained in these slides. So basically, it shows that here we are replacing x with mm, here we are here we are here we are replacing x with Jane. Okay, this is Jane, right? So x with Jane. So in the first case, we are replacing x with Jane, right? For the second case, we are replacing x with OJ and y with John. Okay. In the third case, we are replacing y with John and x with mother of John, right? The last case, actually it fails. To make it successful, we have to use a different variable. So that's what it says, right? Let us not get into this algorithm. We'll we'll just discuss the concepts. Fine. So there is also another way to perform inference in first order logic. So that is by using a rule called generalized modus ponens. So already we have discussed modus ponens. It says that uh, alpha implies beta, and given alpha is true, then we can infer that beta is true. So that is what uh, uh, is modus ponensis. Now here we are discussing something called as generalized modus ponens. With generalized modus ponens also, we can infer directly from the first order logic. So what is the generalized modus ponens? Assume you have a rule something like this: P1 and P2 and P3, so on and so forth, up to Pn implies Q, right? And so this is basically a rule. All these is a rule. And say that you have some facts. These are facts, and you have some facts: P1 dash, P2 dash, P3 dash, up to Pn dash. Okay, right? Then for every P1, you have a equivalent P1 dash. For P1 can be replaced with P1 dash, P2 P2 dash, P3 P3 dash. Like that, for every P1, you have a equivalent something. Okay. So with that, you can identify the theta. So theta is something which we are going to. So see, this P1 will have some variables. They have some variables. These variables should be replaced with some ground term, right? So using this theta, we can do that replacement, right? Using this theta, we can so once you are able to identify, like uh, like P1 should be replaced with what, and P2 should be replaced with what, so on and so forth. If you are able to identify that, then we can easily identify the theta. So once you identify the theta, then you can identify the Q theta. Okay. So here Q is the what you call the conclusion part. See, here this is the precedence part, and Q is the conclusion part. So so in Q we are making the replacement. So theta basically means what? There are some variables which we are replacing, right? And what we should replace with theta. So what is that theta? That's what we have to identify. Okay. Let us discuss with an example. So this rule says that there are many P1. So let us consider our statement. What is the statement which we are discussing? King of X and evil of uh, sorry king of X and greedy of X implies evil of X. Right? King of X and greedy of X implies evil of X. So these are already available in the knowledge base. And what else is available in the knowledge base? We have a statement king of John. It is also in the knowledge base. And we have a statement greedy of Y, which means everybody is greedy. Okay. So now you see this statement king of X and greedy of X implies evil of X. This statement is basically similar to this statement. Here we have many P1, P2 up to Pn. Here we have two terms, that's all. But basically they are same. So if you equate this with this, then what is our P1? Our P1 is nothing but king of x, right? And what is our P1 dash? P1 dash is this x should be replaced with some ground term. So is there any such info in the knowledge base? Yes, we have something called as king of John. So this is P1 dash. So P1 dash is king of John. Okay. And what is our P2? Our P2 is greedy of y. P2 is, or okay, this as per this P2 is greedy of x. P2 is greedy of x. Okay. And what is P2 dash? P2 dash is, here we have a in the knowledge we have a truth which says that greedy of y. So this greedy of y, which means what? Greedy of y means everybody is greedy. From this we can directly infer that greedy of John. From this we can directly infer that John is also greedy. Okay. Now what is Q? This is Q. Here the equivalent thing is Q is evil of x. Evil of x. Right. Now what is our theta? Now what is our theta? What x should be replaced with what, and y should be replaced with what? So here in king of x, here we are replacing x with John. Okay. Here also we have x, but first this x is converted to y as per the rule. This y is also a variable. So basically, actually we are converting this y to, actually we are replacing y also with John, right? So x is also replaced with John and y is also replaced with John. So theta is what? Theta replaces x with John and y with John, right? Now what is our q? Q is evil of x. So what is q theta? Q theta is nothing but in q replace x with theta. So so x should be replaced with what? John. So which is nothing but evil of John. Okay. So this is how generalized modus ponens works. So using generalized modus ponens also we can perform the inference. Okay. So right. So I think we can stop here for today's discussion. So still we have to discuss the what you call, we have to discuss the uh, forward chaining, backward chaining, and resolution in first order logic. That we will continue from the next lecture. So thank you.